Today, I'm here at Men's National Golf Championship, where it's full of swinging clubs, flying balls, and a lot of colored shirts. I know. Golf is probably the most boring sport known to man. It'll put you to sleep like that. Well, not today, because we're going to teach you all the physics incorporated in it, and all the physics behind it, and you're going to learn stuff, and it's going to be fabulous. Now, without further ado, my name is Christopher Yin, and this is
Sport meets Physics!
Look at this guy coming out the putt, alright? It may not seem like it, but the situation is teeming with physics concepts. We can know so much from just mathematical manipulations and some basic physics concepts. Once a golfer hits the ball, we'll be introduced to one of our star players of physics. Are you ready? Good.
Fantastic! Just look at that form! Great googly moogly, this is phenomenal stuff. Did you see that motion? Just watch it accelerate.
I'm so excited, I'm going to introduce our starting lineup, kinematics. What is kinematics, you ask? Kinematics is the study of motion independent of the causes. It consists of several components that you need to know. The first includes initial velocity, final velocity, time elapsed, acceleration, and displacement. With these tools, you can find out virtually everything there is to know about motion. Alright, so we have our givens set out, and we have our equations. Now we're just going to substitute, alright? So we knew that the initial velocity was 2 meters per second, and that the final velocity is 0.7 meters per second, which makes sense because the ball is slowing down due to friction between the ball and the ground. And we calculated displacement, to be 3 meters, alright? We don't know that yet. So we know 3 is equal to 0.7 plus the initial, so that gives me average velocity, times time. Now we're going to solve for time. I'm going to punch into my handy dandy calculator. Oh yeah. And we're going to get t equal to 2.22 seconds. Alright, now that we have that, we just need to find our acceleration. And so we have the one that's missing time. So it has 3 components that we already know, and the final one that we want to find out. Alright, so you plug in v final squared is equal to v initial squared plus 2 times acceleration times displacement, which is 3, that gives us 6a is equal to 4, negative 4, 0.49. And then if you do that, your acceleration should come out to negative 0.585 meters per second squared.
Now check out our next player. His name is Forrest, and he's ready to push and pull some stuff around. Or not. Check out this ball just sitting there, waiting to be struck by that heavy club. Little does he know that there are brave forces acting upon him as we speak. That little voice of doubt might be piping up in the back of your head asking, hold on, how can there be force when there's no motion present? Easy.
So this is how you find some of the forces, or the forces on an object. You first have to draw a free body diagram. Alright, and all that means is that you draw the object, so in this case it's our ball, and he's lying on the ground, okay? And you find all the forces that are acting upon it at that moment in time. So we're assuming this is a horizontal line, so there's no force going on the x-axis. This is our y-axis. And so you know that there's gravity, the force of gravity, acting upon this ball. But there's also F sub n, which is the force of the normal force, which is basically pushing perpendicular to the surface against the force of gravity. So that way, it's not in motion, but there's still forces acting upon it.
Let's look at this next play. Uh-oh, it looks like someone got stuck in a sand trap. I don't really care because I don't follow the game. But what's this? The ball is starting to move. How is that possible? This is a great example of the first law of motion provided by Sir Isaac Newton, or as I prefer to call him, the Newt. As you see, Newton stated that an object at rest will stay at rest and objects in motion will continue to move with the same velocity unless acted upon by an external force. See, the ball is at rest when it's sitting there in the sand, but once a club exerts a force, it begins to move and would continue to move in the same direction with the same magnitude until acted upon by another force. In this case, those other forces are gravity and air resistance. Let's move on, shall we?
Hey guys, I'm dressed up like Isaac Newton because he's my role model. Alright. Gotta erase this. So, what Newton's second law suggests is that the sum of the forces is equal to the mass times acceleration. And this is because whenever you have a non-zero force, the acceleration is always going to be in that same direction as the force. And so, we're going to add, in this situation, the golf ball is affected by air resistance. It's also in free fall due to gravity, or it's falling because of gravity. And so we add these two values together, so we get our net force. So we get Fg minus Fa is equal to mass times acceleration. And then we substitute, so we know these two values in the given. And we also know the mass. And so we can simplify as a basic algebraic equation. So A is going to be 7.6 meters per second squared in the downward direction. Okay? And that makes sense because the net force is going to be less because there is a air resistance counteracting the force of gravity.
As with any sport, there is some risk involved. Now watch these two golf carts racing down the road and BAM! Car A slams into car B.
Alright, here we got Newton's third law of motion. Okay? So, in our example we had car A and car B. And car A slams in to car B. And so what Newton's third law of motion states is that for every action there's an equal and opposite reaction. So if we separate the two and draw them separately, then here is car A's force. This is force applied, 1. And then car B exerts an equal and opposite force on car A. So F1 is equal to F2. And that's what Newton's third law.